Welcome to massive open online course on fluidization engineering. Today's lecture will be on minimum fluidization velocity of fluid solid system. So, before going to that minimum fluidization velocity, we have to know something about terminal velocity of the particle, because this terminal velocity of the particle has a immense role whether the fluidization will be occurring or not, because beyond this terminal velocity, of course, fluidization will start. So, what is that terminal velocity of the particle in the fluidized bed in a fluidized manner, that you have to know. So, this is basically the velocity at which the particle falls freely through a fluid, and at the terminal velocity the weight of the object is exactly, object or particle you can say here, is exactly balanced by the upward buoyancy force, and of course, it will be balanced by the drag force. And here see, if we consider that the weight of the particle as W, and the buoyancy force is denoted by F B here, and drag force is represented by F D, then this weight of the particle will be balanced by the summation of these two forces like F B and F D. F B means buoyancy force and F D means drag force. What is drag here? Drag is nothing but a force acting opposite to the relative motion of any particle moving with respect to surrounding fluid. Now, what is that? How to calculate this weight of the particle W? This weight of the particle is nothing but mass into gravitational acceleration. How to calculate mass? If we know the volume of particle, what will be that volume of particle? If we know the effective diameter of the particle dP, then pi by 6 into dP cube, it will be the volume of the particle, and density of the particle is rho p, then volume into density, then it will give you the mass of the particle. Then mass of the particle into gravitational acceleration g, it will give you the weight, that means that force that will be acting downward, that is under gravity. And F B is the buoyancy force. What is buoyancy force? Buoyancy force is the force that is applied on a particle by the fluid. What is that actually? This buoyancy force is nothing but how much volume of fluid is displaced by this particle. Of course, the volume of the fluid will be displaced by the volume of the particle. So, what will be the volume of the fluid that is being displaced by the particle is pi by 6 into dP cube, and then this mass volume that will be considered for fluid volume by which the buoyancy is acting on the particle. Now, this volume into density of the fluid, then you will get the mass of the fluid, then into g, this gravitational acceleration. So, this mass into gravitational acceleration, it will give you the buoyancy force here. This mass will be the how mass of the fluid that is displaced by the solid particle. And then F D, that is drag force. Two types of drag force you will get. Sometimes you will see for a very laminar region, that means flow is under terminal condition, means the fluid is acting on the particle when particle is going downward under its that is normal normal gravity, that is called a terminal condition. That means there the velocity, whatever it is, it will be less than 0.2 for Reynolds number. So, Reynolds number of the particle, if it is less than 0.2, then the drag force will be calculated as this by Stokes law, that will be equals to 3 into pi into mu into dP into terminal velocity. So, under this terminal velocity, what will be the drag force? This will be 3 into pi mu dp into ut, and this is applied only for Reynolds number if it is less than 0.2. What is that Reynolds number? Reynolds number is nothing but this what will be the inertia force under this terminal velocity, and it will be inertia force, and it will be ratio to the viscous force. So, Reynolds number is nothing but inertia force to the viscous force. Now, this Reynolds number of particle will be calculated based on this particle diameter here. So, Rep will be nothing but rho u dp by mu. Now, if suppose Reynolds number is greater than 0.2, or it is generally for Levenspiel told that it will be if it is greater than 500, then this drag force will be calculated by this. Here this drag force will be directly related to the kinetic energy of the fluid at which this moving under this terminal velocity. Now, what will be the, and A is the projectional area of the fluid particle, and ut is the terminal velocity of the solid particle. So, rho f ut square, that will be equal to rho f, half of rho f into ut square. This is called kinetic energy by which this solid particle will be moving downward or upward or any, that is under this terminal velocity. Now, so this drag force, the drag force is directly related to this kinetic energy, projectional area of the particle. Then, if what will be the then proportionality constant, that proportionality constant will be equal to C d, that is called drag coefficient. So, F d will be equals to C d into half of rho f ut square into A. So, this will be equal to drag force. So, drag force this is under the condition of Reynolds number is greater than 500. Now, how to calculate this projectional area? If it is spherical particle, of course, this projectional area of the particle will be equal to, that is cross sectional area of the particle, that means pi by 4 into dp square. This is your cross sectional area of the particle. If it is spherical, of course, this will be pi by 4 into dp square. Now, if we equalize these forces as per this equation, W is equal to F b plus F d, then we will get here. So, W here, if we substitute here for W, that will be equal to pi by 6 dp cube rho p into z, and F b, this F b will be equal to this here pi by 6 dp cube rho f into z. And then F d, this F d is the drag force. If we consider it as under, that is Stokes flow, then that means here if Rep is less than 0.2, then it will be 3 pi mu dp into ut. Now, if we simplify it or rearrange it, then you will get the terminal velocity under this Stokes flow, that will be ut will be equals to z dp square by 18 mu into rho p minus rho f. So, here of course, this by this equation you can calculate what should be the terminal velocity under this Stokes flow. This Stokes flow will be considered if Rep less than 0.2. Here see one particle, this on this particle, this is one W force is acting, and then what is this drag force is acting and buoyancy force acting. So, this buoyancy force and W, that means weight of the particle, if it is going downward, of course, it will be relative velocity to be W minus A b. This is called effective weight of the particle, or you can say apparent weight of the particles. This apparent weight of the particle will be balanced by the drag force. This drag force, the direction of the drag force will be opposite to the particle motion. So, if we balance same similar way, it is nothing but W minus A b will be equal to apparent weight. So, sometimes in different reference books they are directly related as that apparent force will be equals to drag force. So, apparent force will be calculated as W minus A b. What will be the relative force of weight and buoyancy force. So, by this way we can calculate then terminal velocity under this Stokes flow, that is if Reynolds number is less than 0.2. Now, if Reynolds number is greater than 500, that is it is not Stokes flow, that means under turbulent flow, then of course, you have to substitute the drag force as C t into half of rho f u t square into pi by 4 into dp square. So, this is your drag force at turbulent condition, that means Reynolds number of the particle if it is greater than 500. Now, this see Reynolds number how it is defined here, this is density into velocity into particle diameter by mu, mu means viscosity here. So, mu is the viscosity, rho f is the density of the fluid, u is the velocity, dp is the particle diameter. Now, again if we substitute this w as this weight of the particle as pi by 6 into dp cube into rho p into gravitational acceleration, then you will see this will be your volume, this will be your density, and volume into density will give you the mass into g, that is weight of the particle, and this is buoyancy force. Again the same way, this buoyancy force, how much volume will be displaced by the particle into its density into gravitational acceleration. This will be buoyancy force, and drag force under this condition of REP is greater than 500. After rearrangement and simplification, you will see this terminal velocity at this terminal turbulent flow will be calculated as here just 4 g dp by 3 c d into rho p minus rho f divided by rho f whole to the power half, that means a square root of this. So, in this way at turbulent condition we can calculate what should be the terminal velocity of the particle, and then okay, we will represent this terminal velocity and also particle diameter as a dimensionless form. So, what will be the dimensionless particle diameter and terminal velocity? Why we should do this? Sometimes some references you will see that it is easier to actually represent the flow regime and also the flow behavior by this dimensionless number. So, okay, we can define this dimensionless number of this dp, that is particle diameter, as dp star. This dp star will be into dp into this rho z into rho s minus rho z into z by mu square. Here rho s is the solid density and rho z is the gas density. If you are considering the fluid as a gas, then you have to say here you have to consider this gas density as rho z, whereas mu square is also the gas viscosity. If it is air, then of course it will be air viscosity. So, dp will be defined in this way, dp star, this is dimensionless diameter. After rearrangement you can get it here, this totally here it will be Archimedes number to the power 1 by 3. Here this portion dp cube into rho z into rho s minus rho z into z by mu square, it is called as Archimedes number. Already we have defined earlier this Archimedes number. So, this Archimedes number here it will be 3 by 4 then c d into R e p square to the power 1 by 3. This is one form. Now, u star that means here you can define it as u into some dimensionless number, here see rho z square by mu into rho s minus rho z g to the power 1 by 3, then it will be R e p by Archimedes number to the power 1 by 3, and that will be equal to 4 by 3 into R e p by c d to the power 1 by 3. So, in this way this u star will be defined. What is that u t star? U t star means what will be the dimensionless number of the terminal velocity. This terminal velocity of this dimensionless form will be equals to, like here, this 18 by dp square plus 2.335 minus 1.7445 s by dp star to the power 0.5. So, this terminal velocity you can represent in terms of this dimensionless number of particle diameter as this. Of course, it will be valid or it can be calculated within the range of 0.5 to 1 for sphericity. And then here ut star will be equal to then u 18 by dp star square plus 0.519 by dp star to the power 0.5 to the power minus 1. This will be for if sphericity will be equals to 1, like for a spherical particle. So, here it is important to know that what will be the terminal velocity at its dimensionless form, what should be the particle diameter at its dimensionless form. So, this will be actually used later on for a different aspect. And then terminal velocity, this terminal velocity you can represent this terminal velocity graphically also. Now, if we represent this terminal velocity by this graph shown here in the slide, see here in the x axis, the dp star is denoted as dp will into rho g rho s minus rho g by mu square g to the power 1 by 3. So, and y axis, this is ut star, that is for terminal velocity, what should be that ut into this. So, by this how this ut, that is terminal velocity, will be related to the particle diameter. You will see here ut star, if you consider here, see the ut star will be changing with dp for different sphericity. For different sphericity, you will see for sphericity is equal to 1, this line will give you the different data of terminal velocity for different dp, that is particle diameter, and also for different sphericity you will get different terminal velocity. And from the graph it is observed that if you decrease the sphericity, okay, that means if it is deviated from the spherical particle, then you will see the terminal velocity how it will be changing with respect to particle diameter. Of course, the terminal velocity will increase if dp is increased, that means particle size if it is increased, then terminal velocity will increase. Of course, if size is increased, that that means how fast this particles will fall down freely. And for different other shapes like 0.23, you will see this type of terminal velocity. So, from this graph you can easily calculate, you can identify the number of terminal velocity at a different particle size, a different particle diameter. Now, let us discuss about the particle fluid interaction. Now, you will see whenever a particle is flowing in a fluidized bed or it is falling in a fluid medium freely, then you will see the liquid and particle, there will be interaction. Now, there will be some force acting on the particle whenever it will be moving or falling freely. So, we have already seen that there are two types of forces are acting the particle on the particle, like buoyancy force, when drag force. You will see buoyancy force already we have discussed, and Stokes, there will be if it is there, if the particle is falling freely with laminar flow, that means if Reynolds number is less than 0.2, then you will see there will be a force acting on the particle, it is called drag force. That drag force is calculated as 3 pi mu dp into u. And whereas this drag force will be acting whenever it will be moving with Reynolds number is greater than 500 also. In that case, this drag force is called turbulent drag force. This turbulent drag force will be calculated as CD into half of rho f into u square into a. So, of course, you will see there will be a force acting whenever it will be moving down or upward based on the particle size also, and also what will be the velocity on that depends on. Now, what should be the drag coefficient then? From the drag force, of course, you will be able to calculate the drag coefficient, in the previous slides we have seen that here in the previous slide, here you will see this is the drag force, and this drag force is related to the kinetic energy acting on the particle by which the particle is moving, and also the projectional area of the particle A, and this proportionality constant is called drag coefficient. Now, more precisely you can say this drag force will be defined as this drag force divided by area, that means here projectional area by fluid stress, that means here this drag force is represented by Fd, and here projectional area by dp square by 4. This is dp is the particle diameter, and fluid stress will be represented as by rho f u square by 2. So, this will be called fluid stress, or you can say kinetic energy acting on the particle here. Now, by this you can calculate, from this equation you can calculate what should be the drag coefficient. Now, this drag coefficient for the turbulent flow, you will see it will be calculated as what will be the Fd turbulent, and then pi dp square by 4 by 1 by rho f u square by 2. Here you will see u square will be so high, so that the Reynolds number of the particle will be greater than 500. So, in that condition it is seen that this drag coefficient will remain almost constant, and this constant value will be equals to 0.44. So, at the turbulent condition the drag coefficients will remains constant, this is will be equals to 0.44, whereas in the Stokes condition, that means if Reynolds number is less than 0.2, then you will see the drag coefficient as per this equation, it will be represented by this quantity like this CD Stokes will be equals to 24 by Rep. Here it will be depending on the Reynolds number of the particle, of course. Here it will not be remain constant, of course, within this range of this Reynolds number, that is less than 0.2, if it is suppose 0.1, 0.001. So, in that region, that is if Reynolds number will decrease, then you will see CD will increase, that means drag coefficients inversely proportional to the Reynolds number. So, by this equation you can calculate what should be the drag coefficient in the Stokes condition and also turbulent condition. So, drag coefficient you will be able to calculate now. Now, different authors they have actually obtained different drag coefficients from their experimental data, and they made the correlations in different way to represent the drag coefficient. And here see Hyder and Levenspiel 1989, they have proposed a correlation for drag coefficient, and they have represented the correlation as the CD will be equals to 24 by Rep into 1 plus 8.1716 e to the power minus 4.0655 into phi s, and into Rep to the power 0.0964 plus 0.5565 phi s. See here this portion, not only these big correlations, of course, some other part here, this is 73.69 into e to the power this and divided by Rep plus this. So, from this from this correlation, what is seen that if Rep is greater than 0.2, we can easily calculate what should be the drag coefficient from this correlation. And this correlation, from this correlation it is seen that this CD not only depends on the Reynolds number, it depends only also on the sphericity of the particle. See how this sphericity of the particle actually affect on the CD, you can calculate it from this correlation. So, if you have different sphericity and different velocity, of course, diameter, then you can use this equation to calculate the drag coefficient. Even for spherical particles, if suppose phi s is equal to 1, then very simple here from this you can directly obtain the correlations, obtain the value of CD from this correlation, just putting the phi s is equal to 1. So, finally, you can get reduces this equation to this equation. If we put the phi s is equal to 1, then CD will be equals to 24 by REP plus this. So, from this equation you will be able to calculate what should be the drag coefficient. Of course, this drag coefficient correlation is limited to the flow if REP is greater than 0.2. You cannot apply this correlation for Stokes condition, that means REP, that means Reynolds number, if it is less than 0.2. Now, let us see one example here, is that calculate the terminal velocity for the sharp irregular sand particles. If there is a irregular sand particles, then what should be the terminal velocity? And this of course, so this irregular sand particles is allowed to fall in a air medium, okay, that means through air, then what should be the terminal velocity. So, the density of the air will be taken as 1.2 into 10 to the power minus 3 gram per cc, and viscosity is 1.8 into 10 to the power minus 4. This is at standard condition at 20 degree centigrade, whereas this dp star, what is the dimensionless particle diameter, is 160 micrometer, and density of the solid is given here 2.60 gram per cc, sphericity is taken as 0.67. Now, if you calculate the dp star as this here, this is not dp star, it will be dp is 160, then you will see dp star will be equal to 7.28 and ut star will be equal to 1.294, and then finally, terminal velocity will be equals to 88 centimeter per second. So, you can use the equation that what has already been shown earlier, that how to calculate the ut, and then ut star, from ut star you can calculate ut as here 88 centimeter per second. And then okay, we know now what will be the terminal velocity of the particle. So, before going to that minimum fluidization condition, that is why this terminal velocity is required, because minimum fluidization will occur beyond this terminal velocity of the particle. Now, of course, balancing the terminal velocity, that means here the force, that is net force, what is acting downward, you have to balance that net force to get the minimum fluidization. Now, this minimum fluidization, what is that minimum fluidization? That means the velocity at which all the particles are just suspended by upward flowing gas or liquid by balancing the terminal velocity of the particle. Now, at this velocity you will see the frictional force between particle and fluid just counterbalances the weight of the particles, then only you will get the minimum fluidization. The pressure drop through any section of the bed about equals the weight of the fluid and particles in that section. So, at any section you will see pressure drop through any section of the bed, it will be about to equal the weight of the fluid and particles in that section. So, it is happening only for minimum fluidization condition. The bed is considered to be just fluidized and is referred to as an incipiently fluidized bed or bed at minimum fluidization. So, this minimum fluid just balancing or counter balancing the weight of the particles. And then what should be the net force acting on solid particle at this minimum fluidization condition? You will see here one particle, this will be to be fluidized. Now, what are the force? Now, one is buoyancy force is acting on this particle, and that will be calculated, that is volume of fluid displaced by the particle volume into fluid density and then into gravitational acceleration. You can calculate the buoyancy force. And what are the other forces? That will be apparent weight of the particle. Now, this apparent weight is nothing but what will be the actual weight of the particle is this is L A into 1 minus epsilon into rho p into z. What is this? This is not a single particle here, total amount of particle here. What will be the weight of the particle in the fluidized bed? Now, what will be the L? L is the length of the fluidized bed, and A is the cross sectional area of the bed. Epsilon is the void fraction. Void fraction means other than particle, what will be the space there. And then rho p is the density of the particle, rho f is the density of the fluid, and W A is the apparent weight. Now, if this is weight, this is weight means solid weight in the bed. This is length of the bed into cross sectional area, that will give you the volume of the bed, and then 1 minus epsilon means what will be the volume of the solid particles, and into density of the particle, this will give you the mass of the particle, and into z, this will give you the weight of the particle. And buoyancy force, of course, it will be what will be the L A, that means volume of the bed into 1 minus epsilon means this is the solid volume. Now, this solid volume will displace the water volume or fluid volume or gas volume, you can say this gas volume if it is in the gaseous medium, then into z, this will give you the buoyancy force. And what should be the apparent force? Apparent force is nothing but W minus F B, W minus F B, W means weight and this buoyancy is the force. This is the apparent weight. Apparent weight is nothing but here is you just subtract this buoyancy force from its weight, then you will get the apparent weight. So, apparent weight is nothing but L A into 1 minus A 1 minus epsilon into rho p minus rho f into z. And from this apparent weight of the particles, of course, you will get the minimum fluidization. Now, how to get? You have to balance this apparent weight of the particles with the drag force that is acting upward, acting by upward moving gas. So, this will be the drag force will be balanced by this apparent weight of the particles, so that you can get the minimum fluidization. Now, how to calculate the drag force by upward moving gas? This will be, if you know the frictional pressure drop across the bed, and if you know the cross sectional area of the bed, then drag force will be easily calculated here as drag force as frictional pressure drop across the bed into its cross sectional area. So, this will be your drag force here. So, this is total drag force. Okay. So, what will be the frictional pressure drop? That will give you the drag force. So, this frictional pressure drop into cross sectional area, this will be your drag force. And what will be the apparent weight, that is W, that will be equal to this A into LMF. LMF is the length of the bed at the minimum fluidization condition, and this will be equal to 1 minus epsilon f into rho s minus rho g. How to actually this will give you the volume of the bed at its minimum fluidized height into what will be the fraction of solid here 1 minus epsilon m f at this minimum fluidization condition, then it will give you the total volume of the particle inside the bed, volume into then what will be the rho s minus rho g, this will be the apparent density or apparent weight from which you can calculate rho s minus rho g into z. This already calculated in the previous slides, how to obtain this apparent weight. So, if you balance this, that means if you equalize these two forces of this, what is that, drag force and apparent weight, you will get the condition of minimum fluidization. Now, how to calculate the frictional pressure drop? How to calculate the frictional pressure drop? Of course, this delta Pb by LMF is called frictional pressure drop per unit length of the minimum fluidized height. That will be equal to here, this will be 1 minus epsilon mf into rho s minus rho. This can be obtained just by rearranging this previous equation. Okay. So, here delta Pb is bed pressure drop, LMF is equal to minimum fluidizing height, epsilon MF is the minimum void fraction, and rho s is the density of the solid and rho is the density of the gas. Now, at this onset of fluidization, that means minimum fluidization condition, the void is a little larger than in a packed bed condition. Of course, from this packed bed condition, you are just going to suspend the particles to get the minimum fluidization. So, what should be the minimum void is to get this minimum fluidization? So, here actually this minimum void is will correspond to the what should be the void is in the packed bed, so at the minimum condition. So, at the onset of the fluidization, the void is the little larger than in a packed bed, almost equals to the little bit higher, but you can omit, you can neglect also, you can directly consider the what should be the porosity or what should be the void is in packed bed condition, actually corresponding to the loosest state of the packed bed of hardly any weight here. That is why this a little larger than in packed bed condition this void is. Now, thus UMF you can estimate from the random packing data, or better still one should measure it experimentally, since this is a relatively simple matter. Of course, you can calculate the void is experimentally, otherwise you can directly at this minimum condition you just consider what should be the void is at packed bed condition. There will be hardly an error for this if you are taking into consideration of packed bed void is here, but still for accurate result you can of course measure the void is at this minimum fluidization condition. Now, measurement of the pressure drop. Before going to have this minimum fluidization velocity, of course, you have to know frictional pressure drop, then drag force you have to calculate, already you know that what will be the apparent weight of that, then you have to balance these two forces, then you will get the minimum fluidization velocity. Now, what should be the frictional pressure drop, how to calculate or how to measure also you have to know. Now, the frictional pressure drop can be measured experimentally, which can be expressed as here. So, this measured pressure drop will be equal to, there are two parts of the measured pressure drop. You can measure it by manometer or by any electronics device, like you know that pressure transducer, you can use that to calculate the accurate pressure drop across the column. And so, this measured pressure drop will have two parts, one is frictional pressure drop, another is hydrostatic pressure drop. Now, if you consider the gas solid fluidization, you will see the hydrostatic pressure, of course, this density of the fluid as a gas here, it will be very small, and also this hydrostatic part is very negligible compared to the frictional part. So, only here you can say that measured pressure drop you can calculate directly from the frictional pressure drop. That means, frictional pressure drop is equal to the measured pressure drop here. You will see in equation 2 it is seen that measured pressure drop is delta P of bed for frictional part, and also this plus minus rho f into L m into g. This rho f L m into g is nothing but hydrostatic pressure drop. This plus sign stands for upflow of fluid. The last term may be appreciable for flowing liquids, but it can safely be ignored for flowing gases unless one is dealing with the deep beds at high pressure. Of course, at high pressure you have to consider this hydrostatic pressure also. Now, in most cases with gases you can directly obtain the bed pressure drop by considering the frictional pressure drop. So, this frictional pressure drop of the bed will be equals to the measured pressure drop. This is shown in equation number 3. Now, at the minimum fluidization, of course, the onset pressure drop where fluidization starts and the packed bed condition, you will see this diminishes. So, at the minimum fluidization just diminishing the packed bed condition, and then this minimum fluidization can be then estimated from the frictional pressure drop. Okay. Now, this frictional pressure drop, okay, of course, you can measure it experimentally, or without measurement also you can consider this frictional pressure drop. You can estimate the frictional pressure drop from the Ergun equation. Ergun equation will give you directly the frictional pressure drop in a fluidized bed. Here, this what is that Ergun equation? So, by the Ergun equation you can calculate the frictional pressure drop per unit length as this. Here the two parts of this Ergun equation, one is called, this is inertia, and this is called viscous. This is viscous layer and this is inertial. So, this is inertial and this is viscous. This is viscous and inertia. Now, you will see this Ergun equation is giving you the frictional pressure drop per unit length. So, this is a function of viscosity and velocity and particle diameter, even sphericity. So, this Ergun equation you can directly use to calculate the frictional pressure drop. Now, equating these equations 1 and 4, one can write here this part, this 1 minus epsilon mf into rho f minus rho p minus rho f into g, that will be equals to this pressure drop by the Ergun equation. Now, if you rearrange this equation, then you will get this final form of this equation. Now, you can denote this equation, big equation, in different way also, and like this you can simplify this as this equation by 1.75 divided by epsilon m cube into phi s into Reynolds number square plus 150 into 1 minus epsilon f mf, that means minimum fluidization condition, by mf epsilon mf cube into phi s square into Reynolds number into is equal to Archimedes number. Now, see this equation becomes the quadratic equation of the Reynolds number at the minimum fluidization condition. So, this is here see. So, if we equalize the drag force, that is calculated from the Ergun equation with the afferent weight of the bed, then you are getting the quadratic equation of the Reynolds number at its minimum fluidization condition, where this Ergun number Ergun, or this is not Ergun, it is called Archimedes number, or sometimes some references they are represented it as Galileo number. So, this Archimedes number is defined as rho f into rho p minus rho f into dp cube into z divided by mu square. Mu means viscosity here. Okay. And minimum Reynolds number is the rho f u m f into dp by mu. So, if you solve this quadratic equation, you will get the equation for Reynolds number for minimum fluidization condition. So, solve this quadratic equation to get the REMF. From this minimum REMF, you will get the minimum velocity. So, this, if you know this REMF from this equation of 7, and then just after that you can calculate the UMF from this here. What should be the UMF? Then UMF will be equal to UMF from this Reynolds number, it will be equals to RE, it will be equal to REMF divided by rho f dp here into mu. So, from this you will be able to calculate what will be the minimum fluidization velocity. Okay. And then what should be the voidage at minimum fluidization? Of course, to get the minimum fluidization velocity, you have to know the minimum porosity. Minimum porosity. Minimum porosity is represented by epsilon mf. This epsilon mf, how to calculate this epsilon mf? This epsilon mf you can calculate it from, or you can consider from the packed bed condition. Otherwise, you can directly consider this equation which is given by Wen and Yu 1966, that is phi s into epsilon mf q will be equals to 1 by 14, from which you can calculate what will be the minimum porosity here or minimum void is from this equation. So, epsilon mf depends on the shape of the particle. For spherical particles, epsilon mf is usually 0.4 to 0.45, and you will see if the sharp particle is there with the sphericity of 0.67, for 60 micron particle the sphere void fraction will be equal to 0.60, whereas for anthracite coal of sphericity 0.63, you will get the void fraction of about 0.52 at 400 micrometer in size. So, this void fraction depends on the particle size and also its shape. Now, once you know the minimum voidage of the minimum fluidized bed, then you will be able to calculate what will be the length of the minimum fluidized bed. This length of the minimum fluidized bed can be calculated from the mass of the bed. Mass of the bed, what will be the mass of the bed? This will be the what will be the solid particle, and also what will be the volume of the fluid, what will be the volume of the solid. Then you have to add this. Now, how to calculate here? See, mass of the bed will be calculated as density of the bed into volume of the bed. Now, you can calculate it from this. Now, if you consider only the mass of the fluid, then it will be density of the fluid into volume of the fluid. And what should be the mass of the solid? Mass of the solid will be equals to density of the solid into volume of the solids. So, from this you will be able to calculate what should be the mass of the bed. Now, once you know the mass of the bed, if you divide this mass of the bed by the what is that by this area into density of the particle, then you will get this here this minimum fluidized height. Now, special cases, in the special cases of means whether it is very small particles or not, of course, you will see in the special cases of very small particle, the first term of the right hand side of equation 7, that means here equation 7, you just see here this equation 7, what is the quadratic equation of the Reynolds number. To get the minimum fluidization, you will see that the first term of this right hand side of this equation 7 can be neglected for the very small particles. In this case, inertial effect is negligible compared to the other effect. So, if Reynolds number is less than 20, then you can directly calculate the minimum fluidization from this by neglecting the right hand side part of the equation 7. Whereas, for very large particle, this Reynolds number, if it is greater than 1000, first term will be dominating, and hence you can calculate the minimum fluidization velocity from this equation. So, in this case you need of course the value of epsilon mf and the sphericity, and then if you do not know the value of epsilon mf or sphericity, you can still estimate the minimum velocity for a bed of irregular particles as follows. In this case, you have to first rewrite the equation 7 as this here, this equation 7. In this case, as I considering or denoting by here K1 and K2. This K1 is defined as here 1.75 by epsilon mf cube into phi s, and K2 will be 150 into 1 minus epsilon mf divided by this epsilon mf cube into phi s square. So, here this equation, this equation 7 is represented in terms of k 1 and k 2, these two parameters. So, from this you can calculate what will be the minimum fluidization condition for Reynolds number of this. Here it will be as a function of k 1 and k 2, and also it is Archimedes number. So, from this you can calculate the minimum fluidization velocity. Now, k 1 and k 2 stayed nearly constant for different kinds of particles over a wide range of condition. That means, if R E is within the range of 0.001 to 4 thousandths, then you will get the k 1 and k 2 within this range. Now, different investigators they got the k 1 and k 2 value here. Here see when and u they have represented this k 1 and k 2 as 24.51. So, these are actually experimental data, they have obtained these from the experiment, and experiment of course, this whatever this k 1 and k 2 is coming from this equation, it depends on this epsilon mf and phi s. So, with different minimum voidage and of course, with different sphericity, they have done different experiments, and from their experiment they got this k 1 and k 2. Now, using these values for k 1 and k 2, then the minimum fluidization velocity can be obtained as follows. Here see for coarse particle, that means if particle size if it is greater than 100 micrometer, then you can calculate the minimum fluidization velocity from this equation here. In this case, k 1 and k 2 are taken from this Sisters et al. 1984, they got this, and it will be k 1 will be equal to 20.24 and k 2 will be equals to 1161.94. Whereas, for fine particles, if particle size is less than 100 micrometer, then you have to calculate the minimum fluidization from this equation. In this case, k 1 will be equal to 24.51, little bit higher than the earlier one, whereas this k 2 will be equal to, again this k 2 value is higher than this earlier one, it will be 1651.96. This has been given by Wen and Yu. So, different investigators they are getting different results for different sizes particles. Here if particle size increase or decrease, then of course, accordingly this k 1 and k 2 will be increasing or decreasing. In this case, since minimum fluidization velocity is the most important measurement you need for design, and you need to focus of a tremendous amount of experimental condition and data for wide variety of condition for calculating the minimum fluidization velocity. Now, for gas fluidization, the Wen and Yu correlation is often taken as being most suitable for particle larger than 100 micrometer. So, Wen and Yu correlation is very suitable if it is if particle size is greater than 100 micrometer. Whereas, the correlation of Bayes 1974 he has proposed, in this case will be the best for particle less than 100 micrometer. So, this will be your correlation of Bayes that you can directly use for calculating the minimum fluidization velocity. If your particle is being used or you are using particle which is size less than 100 micrometer. So, this will be your suitable correlation to calculate the minimum fluidization. There are other different investigators, they have calculated or they have developed the different correlations for minimum fluidization velocities. These are some correlations that are given here in the slides that you can follow for calculating the minimum fluidization velocity. Now, what are the factors that affect the minimum fluidization velocity? You can see some geometric variables, some variables as a physical properties, some are thermodynamic conditions. Now, geometric variables like bed diameter, bed height, particle size, distributor hole diameter through which the gas is distributed or liquid is distributed. Now, fluid density fluid viscosity, fluid surface tension, slurry concentration, all are the factors that affect on the minimum fluidization velocity. Even some thermodynamic condition at higher pressure, of course, you will see the minimum fluidization velocity will be higher, whereas temperature at lower temperature it will be the higher minimum fluidization velocity. So, these are the factors which affect the minimum fluidization velocity. Okay. Next class will be one example will be given to you for minimum fluidization. Thanks for all today.